All right, everyone, let's get started. Welcome to General Relativity 101. I am absolutely thrilled you're here today because this explainer is going to demystify the ultimate astronomical anomaly, black holes. We're going to strip away the science fiction and look directly at the actual mechanics of the most astonishing places in our universe. Places where gravity is so incredibly intense, it actually breaks reality as we know it.
Okay, let's just dive right into today's syllabus. Our field trip into the abyss covers from theory to reality, visualizing the abyss, distorting space and time, spaghettification and the singularity, and we'll wrap it all up with the information paradox. Section 1. From theory to reality, the mathematics of extreme gravity. To really wrap our heads around this extreme gravity, you have to imagine a truly staggering compression of mass. Think about our own sun, right? Now, imagine taking that massive star and just squashing it down, and squashing it some more until its radius is a mere 3 kilometers. The gravity right at its surface becomes so immense that it fundamentally alters the physics around it. Now, we didn't always know these cosmic monsters were out there. Decades ago, black holes were kind of considered just a mathematical quirk, a weird theoretical solution to Albert Einstein's equations that seemed to fit the math but surely couldn't exist in reality. But then, observation caught up with theory. By the mid-20th century, scientists actually started measuring the warped movement of stars, galaxies, and gases that were orbiting seemingly empty patches of space. Fast forward to 2019, and we captured the very first actual photograph of the massive black hole in the galaxy M87. And the craziest part? We now estimate there are up to 40 quintillion black holes in our universe.
So, what is the defining feature of these things? It all comes down to a concept called escape velocity. Simply put, this is just the speed required to overcome an object's gravitational pull. Because a black hole is incredibly massive but packed into such a tiny space, its escape velocity actually exceeds the speed of light. And since absolutely nothing in the universe can travel faster than light, nothing, not even a light ray emitted from its surface, can escape. It is entirely trapped.
Moving on to Section 2. Visualizing the abyss, the anatomy and scale of the unknown.
Now you might be wondering, if black holes trap all light, how on earth do we take pictures of them? Well, we don't actually see the black hole itself. What we're spotting is its glowing accretion disk. This is just a disk of material caught in that wild gravitational pull, violently orbiting the dark center. As it spirals inward, it collides, heats up immensely, and emits a blinding light. And this brilliantly illustrates one of the most stunning optical illusions in all of astrophysics. Because gravity is so extreme here, it literally bends light. If you look at a black hole from above, it looks pretty intuitive, right? Just a standard glowing ring orbiting a dark center. But viewed edge-on, the gravity bends the light from the back of the disk right over the top and underneath the bottom. You are simultaneously seeing the front, the top, and the back of the accretion disk all at once. Mind-blowing.
And the scale of these objects is practically unfathomable. On the quote-unquote small end, you have J1650. That's a black hole roughly the diameter of Manhattan, with a mass of nearly 4 suns. Then look at our own Milky Way supermassive black hole, Sagittarius A star. It is over 4 million times the mass of our sun, yet it's shockingly compact. If you dropped it right into our solar system, its spatial footprint would only extend to about 1/5 of Mercury's orbit. And then there are the heavyweights. Objects like TON 618, clocking in at an incomprehensible 66 billion times the mass of our sun. Just incredible.
Okay, Section 3. Distorting space and time. The descent begins.
So, what actually happens if we decide to visit one? Class, it is time for our field trip. I want you to imagine we're in a magically insulated spaceship approaching a black hole. We turn our market motors off and just enter free fall. We're floating, much like astronauts on the ISS, completely blissfully unaware of the immense forces we're about to encounter. But here is where Einstein's genius truly shines. Space and time are one stretchy fabric called spacetime, and massive gravity warps it. Because of this, there are actually 2 entirely different realities occurring simultaneously. For an outside observer watching us fall with a powerful telescope, our clocks would seem to tick slower and slower. To them, we'd become infinitely redder, infinitely redshifted, and appear to just freeze forever at the edge, the event horizon. They would never actually see us fall in. But from our perspective inside the ship, time passes perfectly normally. We feel zero disruption, and we just drift right on across that event horizon. Reality outside differs drastically from reality inside.
A really wonderful way to understand this is the river of space-time analogy. Imagine space itself as a river flowing into a giant sinkhole. Far away, the river flows pretty slowly. Right at the event horizon, the river of space is flowing inwards at exactly the speed of light. And inside the horizon, space itself is plunging inward faster than the speed of light. So if you imagine a photon of light trying to escape, it's like a little fish swimming against a tide that is simply moving way too fast for it to ever swim out. And keep in mind, the water in this river moves at drastically different speeds depending on how close it is to that central sinkhole. Which brings us to Section 4, Spaghettification and the Singularity, the breakdown of matter and time.
Now that we've crossed the event horizon, things definitely take a turn for the perilous. We're falling deeper, way past the point of no return, and we finally begin to feel something. The gravity doesn't just increase here, it increases on a drastic gradient. Enter spaghettification. Think back to our river flowing into the sinkhole. The current pulling at your feet is violently faster than the current pulling at your head. This uneven gravitational pull causes extreme physical stretching and squashing from the sides. It sounds like a funny word, sure, but for our hypothetical astronauts, it most certainly is not.
The disassembly process is just brutal. First, the human body gets violently stretched and pulled apart. As we continue to fall into the ever-steepening distortion of spacetime, it gets worse. Individual atoms are separated from one another. Then, the protons themselves are ripped right open. Finally, even the fundamental quarks inside those protons are completely separated. Every single piece of matter is utterly disassembled as it races inward.
But what's truly fascinating is what we are actually racing toward. We're taught to think of the singularity at the center of a black hole as an infinitely dense, tiny physical point in space. But remember, a black hole warps space and time. So the singularity is not just a place. In Einstein's theory, it is a moment in time. For anyone falling in, it represents the literal end of time.
So if you're inside the event horizon and you try to turn your ship around to fire your engines and fly away from the singularity, you can't. Because the singularity isn't just in front of you spatially, it is in your absolute future. Trying to avoid the singularity inside a black hole is exactly like saying, I can't run away from tomorrow. It is temporally impossible.
And that leads us to our final stop, Section 5, the information paradox, quantum enigmas at the end of time. That singularity sounds like a pretty definitive end, doesn't it? For a long time, scientists thought exactly that. Once matter hit the singularity, this story was completely over. But modern cutting-edge physics tells us this cosmic mystery has a whole second act. The legendary physicist Stephen Hawking threw a massive wrench into our understanding when he famously declared, "Black holes ain't so black." He realized that black holes don't just act as cosmic vacuum cleaners that exist and grow forever. See, Hawking discovered that black holes actually emit a very faint thermal glow, now known as Hawking radiation. Because they're constantly leaking this thermal energy, they are slowly losing mass. Now, it takes eons upon eons, but eventually, the black hole will evaporate and vanish entirely, leaving perfectly normal, empty space behind.
But this creates a huge problem for physics. A stark, totally mind-bending question. If a black hole disappears entirely, what happens to the information of everything that fell inside? Think about our spaghettified atoms. The fundamental laws of nature strictly dictate that information in the universe can be scrambled, sure, but it can absolutely never be destroyed.
And there is your information paradox. In Einstein's era, we thought everything was just crushed at the singularity. Then Hawking showed us black holes evaporate via radiation, but his initial calculations suggested that radiation was purely thermal, completely free of information. That meant information was being permanently erased. But then in 2019, a series of groundbreaking papers revealed a subtle mathematical correction suggesting Hawking's radiation is actually not information-free. Somehow, someway, the records of what fell in are miraculously imprinted on the escaping radiation.
So how exactly does information escape an inescapable void? Well, the jury is still very much out, but some theories suggest the interior of a black hole might actually connect to the exterior via microscopic wormholes. Bits of quantum information might just leak out through those tiny quantum tunnels. Other leading theories propose something even wilder, that space and time themselves aren't fundamental, but instead the universe might be best described as a giant, entangled network of qubits, literally like a quantum computer. This right here is why astrophysicists are so obsessed with these dark voids. As physicist Dr. Brian Cox so beautifully puts it, when you study completely collapsed stars, you're gaining insight into quantum computers and networks of qubits. It's the most wonderful thing. By studying the extreme limits of gravity, we aren't just learning about dead stars, we are reverse engineering the foundational structure of space and time themselves. And that brings our explainer to a close. Class, I want to leave you with one final profound question to ponder the next time you look up at the night sky. If the extreme gravity at the end of time inside a black hole reveals that our universe ultimately functions like a giant quantum network, what unseen hidden structures are quietly governing your everyday life right here on Earth right now? Think about it. Thank you so much for joining me for General Relativity 101. Class dismissed.